if we raise 5 kilograms, 6 meters, how much work does gravity do? Well, I'm going to do this in terms of I and j vectors and dot products, although that's not necessary in this case because we're going to be talking about force lifting the object and the force of gravity. Actually, we aren't even going to talk about the force lifting the object yet. We've got the force of gravity, which is straight down. We're going to lift the object straight up. So everything happens along a line. And the only real caveat, the only real thing you got to know here is that gravitational force is in the opposite direction to your displacement, so that whatever the sign of your displacement, the sign of your force is going to be opposite, and you're going to find that gravity does negative work when you raise an object. Now, we're going to do that in a little more sophisticated context. We're going to say that, okay, the work done by gravity is the dot product of the force exerted by gravity and the displacement. So, as this is going to be a very simple dot product, we want to express the force and the displacement as vectors. So the force is going to be what? 5 kilograms times 9.8 meters per second squared in the negative j direction. And then our displacement is 6 meters in the positive j direction, straight down and straight up. Okay. When we do this dot product, of course, j dot j is 1, so we just get the negative 5 kilograms times 9.8 meters per second squared times 6 meters, which gives us negative 294 joules. Gravity does negative work, 294 joules, on a 5 kilogram mass that's raised 6 meters. Now, we're tying this in with the preceding problem. Remember where we had plus 400 joules done by the net work, and I kind of got things backwards there. I said the change in the kinetic energy was 400 joules, so the net work was 400 joules. Well, what you were given in that problem is that the net work was 400 joules, and the change in kinetic energy was 400 joules. Either way, the work done by the net force is 400 joules, and it's worth mentioning that the change in kinetic energy is the same as the work done by the net force. So what we have is now the work done by the net force is 400 joules. The work done by the net force is equal to the work done by the non-gravitational forces plus the work done by gravitational forces. We'd have to agree that if we categorize our forces as non-gravitational or gravitational, that breakdown is inevitable. Okay, if we just have two categories, the work done by the various forces has to be either in one category or the other, the work done by each force. Okay, so this tells us that the work done by our non-gravitational force is equal to our 400 joules minus the work done by gravity. So what's the work done by gravity? Work done by gravity is negative 294 joules, so subtracting that from the 400 joules, we get 400 joules plus 294 joules, or 694 joules. So whatever the non-gravitational force is that causes this object to rise is going to have to do work of 694 joules. That means if I want to raise this object 6 meters, of course my arm isn't long enough to do that. I'm going to have to maybe get up and do something. While at the same time increasing the kinetic energy by 400 joules. So I'm not only raising the object, but I'm speeding it up. I have to do 294 joules of work against gravity. Gravity's doing negative 294 joules. I've got to overcome that with 294 joules of my energy. And another 400 joules to increase the kinetic energy. And that's how this can be understood. Now, we move on into the idea that the work done by gravity results from a conservative force. Now, conservative force, again, you've had documents that explain this, but a conservative, and I think I've assigned some reading. where you would also see this reinforced. A conservative force is a force that's path independent. The example I gave in class is if I raise some object, I don't have anything very heavy, well, this battery's a little bit, okay. If I raise this battery, okay, then gravity is exerting a force in what direction as I raise the battery? Well, downward. If I lower the battery, what force is gravity exerting as I lower the battery? Well, whatever the weight is, downward. Now, I don't know if you can see this yet. If I put this on the wider edge, maybe it'll sit. Okay, if I slide this across a surface, okay, as I slide it this way, friction is exerting a force in this direction on the object. If I slide it this way, friction exerts a force of the same magnitude, but now it's in the opposite direction because the frictional force will always work in the direction opposite that of motion. Okay, so in this case, the frictional force changes as I change my path. If I go from here to here and back, friction acts in an opposite direction, coming back as opposed to going forward. Whereas if I raise the object and lower it, gravity does the same, exerts the same force at every point. If I take an object, this ball, and move it around some path, okay, wherever I move it, and then bring it back to its original point, okay, gravity has exerted the same force at every point of that path. And it's going to follow, and I'll draw a picture in a minute, it's going to follow that the total work done by gravity around that entire path adds up to zero because gravity is doing positive work when I raise the object, negative work when I lower it. And if I take that entire path, I said I was going to talk about that in a minute, I'm going to go ahead now. If I take that entire path, let me draw a little less complicated path, starting from some point and ending at the point, then I can break that path into a bunch of small subpaths. So I'm not going to draw them for the whole loop, but we understand. And on any subpath, I've got a displacement vector that is a pretty good approximation to the net displacement. Well, it does give you the net displacement, but I've got a displacement vector, and I've got a gravitational force vector that I'll draw in some other color. Okay, gravitational force is here. Now here I've got a displacement vector and a gravitational force vector. And here, same thing. Now I can draw these for the entire path. And we should understand that the work done on every subpath is going to be the dot product of the displacement vector with the gravitational force vector. So color challenged here. I could say delta W sub I, the work contribution on the ith part of this path. Okay, if we index these paths from 1 to n, and the work done on the ith path is going to be the product of the gravitational force, well, the dot product of the gravitational force with the displacement vector, delta S sub I. So that the total work being the sum of the contributions of the work contributions from the individual increments into which we've divided the path, total work is going to be the sum of all that. And it takes a little proof, but it's not too hard to believe that since all the up adds up to zero, because we're going up, we're going down, and all the ups and downs add up to 0 as we go around here. And since the work done by gravity is negative as we go up and positive as we go down, it's going to follow that the total of all this work around the entire path is 0. Now, I'm not actually going to probably ask you to do much of this, and I'm certainly not going to ask you to do the resulting line integrals, but this whole process leads to what we call a line integral of the force times the displacement over the little circle on the integral sign means closed path, and that's 0. That's equivalent to saying that the force is path independent, and that's what we mean by conservative force. Now, if I raise this ball and then drop it back to its original position, by virtue of being in the higher position, it has the potential to develop a kinetic energy, and that kinetic energy is equal to the magnitude of the work I did in lifting this. So we've got what I call potential energy. Everybody calls it potential energy. We have potential energy at this point. We have the potential to do work and either perform work or develop kinetic energy or a little of both. Okay, we could use some of that energy to overcome friction. We can use it in various ways. The potential energy, then, we're going to say, is equal, it's equal to the work that I would have to do to raise the object, and that's opposite to the work done by the conservative force of gravity in the example I gave. Now, there are other kinds of conservative forces. Magnetic forces are conservative, electrostatic forces are conservative. Spring forces are mostly conservative, but of course there's a little energy loss there, and we'll talk about that. Okay, so I'm going to define, in any case, motivated by what we said, potential energy change is equal and opposite to the work done by conservative force acting on an object. Okay? Now, I've got this word on here. This means that this force is acting on the object. This is the conservative force acting on the object. When we get into thermodynamics, we'll talk a lot about work done by the object, okay? Work done by a system, which is equal and opposite to the work done on the system. So we want to distinguish on from by. Now, this is by the conservative force, but this adjective always applies to the system, on the system or by the system, okay? Now, everything we see here is going to be on for a while. So the potential energy change is equal and opposite to the work done by conservative forces on the system. Now, how does that fit into the scheme we have here? Well, simply that then the work done by the net force on the system can be broken into the work done by NC non-conservative forces on the system and the work done by conservative forces on the system. And conservative forces acting on the system do work that's equal and opposite to the potential energy change. So this is replaced by negative potential energy change, and now we have work done by non-conservative forces on the system. Okay? Now, the net force, work done by net force on the system is equal to the change in kinetic energy. Work done by the net force on the system is the work done by conservative forces plus the work done by non-conservative forces, which is the work done by non-conservative forces. I think I said that wrong, but you understand. It's the work done by non-conservative plus the work done by conservative forces. That's equal to the work done by non-conservative forces on the system minus the potential energy, so that we replace the delta W net on here by this expression. And now we conclude that the work done by non-conservative forces on the system is equal to the change in the kinetic plus the change in the potential energy. So I do some work on the system. My work is non-conservative. That work can go into changing kinetic energy. It can go into changing potential energy or any combination thereof. This, once you get used to it, it's a profoundly powerful idea.